Welcome to Visual Algebra Lecture 8.2, Examples of Rings. Though it's well known that there are only two groups of order p squared for any prime p, the fact that there are 11 rings of order p squared is fairly obscure and almost never done in a book or class. In this video, we'll explore all 11 rings of order 4 using their Cayley tables, subring lattices, ring presentations, and matrix representations. It's interesting that the 8 that have a non-cyclic additive group structure have different subring lattices. Recall that this concept was introduced in the previous lecture, and it's basically the subgroup lattices where the three different substructures, ideals, subrings, and subgroups, are annotated by color. Though seeing all rings of order 4 is not necessary to do in ring theory, it is interesting and worth seeing. If you want to know more, I encourage you to check out my recent Math Magazine article on finite rings, which is appearing in print in the same month in 2025 that I'm recording this video. We'll finish this lecture with a brief discussion on how many finite rings there are of various small orders and with certain properties. Finally, we'll finish with some more standard examples of infinite rings and some of their subgroups, subrings, and ideals. Okay, let's get started.
Let's start with the concept of a subring lattice, which I introduced in the previous lecture. This is non-standard. It's my own definition and own convention, but we're going to rely on it heavily in this lecture. To make a subring lattice, we start with the subgroup lattice of the ring, and we color code the subgroups as follows. Ones that are ideals, we color in blue. Ones that are subrings but not ideals, we color in red. And ones that are subgroups but not subrings, we color in gray. Here are two examples, and we saw these both in the previous lecture, and we did this one in more detail. Let me just remind you. So if you take the subgroup generated by 1, 0, that's 0, 0, 1, 0, 2, 0, and if you multiply by anything of the form A, B, you're going to get something of the form A, 0, which is in here. So this is an ideal. This is a subring, because this contains 0, 0, 1, 1, 2, 2. Again, remember this is how I write ordered pairs. And then if you multiply this, now this is closed under multiplication, but if I multiply it by something of the form AB, I get A, 0, which is not in here. And finally, 1, 2 generates three elements. Let's write them out up here. 0, 0, 1, 2, and you add this to itself, you get 2, 4, which is 2, 1. And this is not even a subring because 1, 2 times 2, 1 is 2, 2, which is not in here. And this one I'm going to let you explore for yourself. This is the group Z2 cross Z2 cross Z2. Now let's move on to exploring the rings of order 4. 3 of them have an additive group which is cyclic, Z4. So here is the Cayley table of such a ring, and here is the subring lattice, as we will see. The first one is just plain old Z4. So Z4 under multiplication, you can think of A as being 1. So 1 times 1 is 1. 2 times 2 is 4, which is 0. 3 times 2 is 6, which is 2. And here's two other ways we can represent this ring. The first one is with something called a ring presentation. And I'm not going to spend, I don't think, any time on this outside of this lecture. I encourage you to check out Benjamin Fine's 1993 article on finite rings that appeared in Math Magazine, where he introduces this concept. And he classifies all 11 rings of order 4 using these. Now, in my 2025 article on finite rings, I go back and I review this and I include the Cayley tables and the subring lattices, but I do mention these in addition, though I don't derive them in the way that he does in 1993. So here's another way to represent this ring. You can think of this as these four matrices, and if you just the scalars of the identity, and if you multiply them or you add them together, this is the table. If you multiply them, you get this table. Here is the second ring whose additive group is cyclic. You can think of 0, 1, 2, and 3 and just double it to get 0, 2, 4, and 6 and have this sit inside of Z8. So I write this as 2Z4, which is a little bit dangerous on its own. But if I only write this when I put the larger ring here that contains it, then it becomes non-ambiguous. So here's the ring presentation. Here is the Cayley, the multiplicative Cayley table. And you can think of this as these four matrices right here, which once again are 2 by 2 matrices over Z4. Finally, if we take this original ring and we quadruple the elements to get 0, 4, 8, and 12, and think of this as sitting inside of Z16, we get this last ring that has really a trivial multiplication table. We saw an example like this in the previous lecture for Z6, and here is the ring presentation for that. So 4 times A is 0, and A squared, the square of everything, is 0. You can think of this ring as consisting of the following four matrices, so zeros everywhere but a 0, 1, 2, or 3 in the lower left corner. And this is a subring of all 2 by 2 matrices over Z4. So all of these have the following subring lattice, and that's because this is the subgroup lattice of Z4, and the entire ring and the trivial ring are always ideals, and it turns out that in these four cases, this ring generated by 2A will be an ideal as well.
Let's move on to the 8 rings whose additive group is non-cyclic. Here's the additive Cayley table. 3 of these have unity. They are the finite field of order 4, which we'll learn more about later in this chapter when we get to finite fields. There's Z2 cross Z2. That's the group where multiplication is just defined component-wise mod 2. And then there's one more that I don't know what to call, but it's generated by the identity matrix 2 by 2 and the all ones matrix over Z2. So let's start with the finite field F4. So here's a multiplicative Cayley table. Notice that A is the multiplicative identity. Think of that as 1. And A will be that identity element for all of these. And then what else do you notice? So A has order 2. It generates a subring because it's closed under multiplication. You can see that 2 by 2 block right here. Now B and C, B squared is C and C squared is B. So these do not generate. So the subgroup generated by B, that is 0 and B, is not closed under multiplication because it's got a C here, and same with C. So these things are not even subrings, but this one is. And finally, you can represent this finite field with these 4 2 by 2 matrices over Z2. Next, we come to Z2 cross Z2. So this is a subgroup that we're very familiar with, but now we are putting a multiplicative structure on it. And A is the identity, so that's the element 1, 1. And that is a subring because it's closed under multiplication. And now let's look at B. So you can think of B as being 1, 0. That is an ideal because if you multiply B, not only is it closed under multiplication because these 4 entries are within 0 and B, but B times anything gives you either 0 or B. And C times anything gives you 0 or C. So these things are both ideals, and here's that subring lattice. And you can represent these with these 4 by 4 matrices over Z2. Notice it's like the identity matrix with the 1, 1 entry and then the 2, 2 entry. Finally, we come to this last ring, and so A is the identity matrix. Well, here are the elements. So B is the all ones matrix. If you multiply this by itself, you get the matrix 2, 2, 2, 2, which is 0 if you're over Z2. And then C squared, this matrix times itself, is the identity matrix, which is A. And so the subgroup generated by C, just these 2 elements, is not closed under multiplication because C squared is A. So that's not even a subring, that's a subgroup. And then the one generated by B, that is an ideal because B times anything is just 0 or B. So that's an ideal. And then, as I said before, the identity matrix generates a subring. Here are the 3 rings with non-cyclic additive group, which are commutative and do not have unity. So first is the ring with trivial multiplication, where the product of any two things is 0. You can think of this as consisting of the following ordered pairs, 0, 0, 2, 0, 0, 2, 2, 2, where everything is done mod 4. So I like to call that 2z2 squared, but you can't say that without saying that it's a sub where it lives. And you can think of this as these 2 by 2 matrices right here. Here is the subring lattice. And notice that all of these are ideals trivially because, if you multiply any element here times anything, you get 0. So of course that will be contained in the subgroup that it generates. Next we have this ring, which I call Z2 cross 2Z2, but I have to specify that that lives in Z2 cross Z4 for that to even make sense. So this consists of the ordered pairs 0, 0, 0, 2, 1, 0, 1, 2. I cannot think of a way to represent this with 2 by 2 matrices. It doesn't mean there isn't one. It's just I couldn't find one. So please let me know if you can think of a way to do it. Just write something in the comments. Again, it would not surprise me if there was one. It's just it didn't seem to fit the pattern of the previous ones. And I didn't spend too much time on it either. So here is the multiplicative Cayley table. So A, B, and C all generate size 2 subgroups. So the question is, are they closed under a multiplication? Well, A and B generate ideals because these things times anything either give you 0 or the element itself. So one of these is A, one of these is B. And then C is the subgroup generated by C is not closed under multiplication because C squared is B. So looking back over here, well, which is which? So 0, 2 squared is 0, 0, because we're doing things mod 4 in the second coordinate. So this is A. B squared equals B. That has to be this one. And then the next one has to be C, because C squared equals 1 comma 4, which is 1 comma 0, is that one. So here's the subring lattice. And now here's the last ring right here. And you look at the Cayley tables, and it's tempting to say that, oh, maybe these are isomorphic because the tables have the same structure, right? Well, not so quick, because this one up here has one element that we say is idempotent. That means the square of it is equal to itself. That's B. There's no elements down here other than 0 that are idempotent. The square of any element is going to be something else. So I call this R sub j, and it can be represented with 3 by 3 matrices. And once again, maybe there's a way to do this with 2 by 2. I could not come up with one. Let me know if you can. I don't know how to prove that you can't do it with 2 by 2 matrices. Maybe there is a brute force or a simple proof. But I call this RJ because this is a Jordan block in linear algebra, and this generates all the non-zero entries, or actually all the entries, because if you square this matrix, you get this matrix right here, J squared. And then if you cube the matrix, or if you add these together, you get J plus J squared. So let's try to figure out which, so these 3 elements you can think of as being 0, J, J squared, and J plus J squared. So which one is which? Well, if you take this element and you square it, you get 0, right? So that means that this thing so A has to be J. If you take this element J and you square it, you get J squared. So that means that, well, J squared is one of these things, but which one is it? I'm actually not sure. You could check just using this table. I don't think you need to do it. But anyways, looking at this, you can tell that 2 of these are not even subrings because the subgroup generated by B is not closed under multiplication because B squared is A, and nor is the one generated by C because C squared is A. So A generates an ideal, but the others do not, and so this definitely is different from this because it has a different subring lattice. Finally, here are the last 2 rings of order 4 that have non-cyclic additive group. And both of these are non-commutative. Each one is the so-called opposite ring of the other. And I think it should be clear what I mean by this if I just show you the multiplicative tables. And I'm going to abuse notation a little bit. And for these, we have left ideals that are not right ideals, or vice versa. So non-two-sided ideals. And I will write these in purple. And I'll use this notation with an open parentheses on the left and a bracket on the right for a left ideal that is not a right ideal, and vice versa. Don't worry, this is the only place in my video series and in my book where I use this notation, and I just do it so I can do something for this subring lattice. So you can think of this ring here just as these four matrices, 2 by 2 matrices over Z2, and the opposite as the transposes of them. And you can check that the subgroup generated by B is an ideal because B times anything is 0, and then anything times B is either 0 or B. And then A and C, let's just do one of these. So A times something is not contained in the subgroup generated by A, so that is not a right ideal, but anything times A is going to be in that subgroup, so that is a left ideal. And then the opposite ring is just completely analogous. Just take the transpose of everything here, these matrices, the table, and this diagram. In general, we'll be more interested in infinite rings than in finite rings. But I think it is worthwhile to see those examples that we just did, just to walk into the cave and shine the light around and see what sort of things there are. But I do want to say a couple more words about finite rings, mostly for fun. Here's a table showing how many groups, rings with 1, rings, and non-commutative rings there are for each order 1 up to 12, and then also 16 and 32. Let's make several comments. First of all, small non-commutative rings with 1 are rare. So non-commutative rings, I guess I have here, but I haven't told you how many of them have unity. So there are 13 of them of size 16. So there's 228 non-commutative rings, but only 13 of them have unity. And then there's one of them of size 8. So 1 out of these 18 have unity. And then there's one of size 24 and 27, which I haven't put on here. And then there's no others of order less than 32. Which I think is pretty interesting. What else do you notice? So there's just not many non-commutative rings in general, except for things where there's a power of 2 here, or there's 12 has a square that divides it. And notice how the vast majority of rings do not have unity. So rings with, there's 50 rings of order 16 with unity, but there's 390 without unity. So I think that's interesting. And also, notice how I have I say of order 32, there's at least 18,590. Last I checked, this number is not known. This is an open problem about how many rings there are of order 32, which I find remarkable because that is completely not open for groups, And then this question mark down here, I don't even know if there's a good estimate for that. So I think I Googled this, of course, and I found this lower bound, and then I couldn't find anything about this right here. Here's something else that I want to show you, mostly for amusement purposes. For distinct primes P and Q, assuming P is at least 3, here's how many algebraic structures there are. So for groups and rings. So there's one group of order P, that's cyclic, and there's 2 rings of order P. There's ZP with a multiplicative structure, which is a finite field. And then there's the ring where multiplication is trivial. Product of any 2 things is 0. So for order P squared, there are 2 groups. There's a cyclic group, and then ZP cross ZP. And then for rings, there's 11 of them, and we just saw 11 of order 4, and that pattern generalizes for arbitrary primes P in the predictable manner. Finally, groups of order P cubed, there are 5, and for rings, there are 3P plus 50. I find that fascinating because I have no idea. I mean, this is not constant. It depends on P, and it's precise. So yeah, I don't know why this is or how to classify them, but I'm sure somebody knows, and it's some rabbit hole you could go down. And most of these things I think hold for general P and Q, but this one particular one requires P to be at least 3. And then rings of order PQ, there are 4 of them. And we saw the 4 rings of order 6 in the previous lecture, and that pattern also generalizes predictably. And then of order P squared times Q, I don't know a good pattern for groups. But there is no more than 5. But and I think that depends on what primes they are. Sometimes there's a semi-direct product, sometimes there's not. And then finally, there are exactly 22 rings of order P squared times Q. As I said earlier, most of the rings that we will see in this course are infinite, but there are 2 finite rings that we will occasionally encounter, and those are Zn and finite fields. Let's now see some examples of infinite rings. We'll start with ones that we're familiar with. The integers is a ring that's contained in the rationals, that's contained in the reals, that's contained in the complex numbers. All of these are commutative rings with 1. For any ring R with 1, or actually even without 1, the set of n by n matrices over R is a ring. We'll either write that as Mn of R or Matn of R like we did earlier. This will have an identity element, which is the identity matrix, if and only if R has 1. For any ring R, if you take the set of functions from R to itself, that is a ring by defining addition and multiplication as you normally would with functions, like if these were sine or cosine. The set of even integers is a subring of the integers, but it does not have unity. So a subring does not have to have unity just because the big ring does. But it gets even weirder. Let's consider the set of 2 by 2 matrices where there are 3 0 entries, everything but the top left corner. That is a subring of the 2 by 2 matrices over, say, the real numbers. However, the identity element in the ring is the identity matrix, but that does not live in this subring. However, this subring does have an identity element, which is this matrix here, 1, 0, 0, 0. So subrings could have different multiplicative identities than their parent ring. And that is not going to be the case for the additive identity, because we know that's not the case for groups. Finally, if R is a ring and X is a variable, we can define the polynomial ring over R exactly how you would expect. So that is the coefficients are from R. Near the end of the previous lecture, we saw some examples of the 3 types of substructures that we learned about in rings that are subgroups, subrings, and ideals. And remember that I color them blue if they're ideals, red if they're subrings but not ideals, and gray if they're subgroups but not subrings. Let's now see some more examples of this in the polynomial ring over the integers. Let's start with subgroups that are not subrings. So if you think about this set of polynomials just as a group, then X generates a subgroup. This is an additive group, so we just take X and we add it to itself as much as we want. And its negatives, which are its inverses. So that consists of all integer multiples of X. And that's a subgroup, but it's not a subring because it's not closed under multiplication, because X times X is not in this set. Similarly, if we take the subgroup generated by 1x and x squared, we get all degree 2 polynomials, or degree 2 polynomials or less, and that is not a subring either, because if you multiply x squared times x squared, you get x to the 4th. Let's now see examples of subrings that are not ideals. And once again, think about this set of polynomials as an additive abelian group. 2 generates a subgroup. You can add and subtract it to itself however many times you want, and you get the even integers. That is not an ideal, because if you take this set and you multiply by x, you no longer have an even integer, you have a degree 1 polynomial. Here's another example. Let's take the subgroup generated by 1, x squared, x to the fourth, etc., say an infinite generating set. And again, you can add and subtract these at will. What do you get? Well, you get all polynomials that have only even powered terms. So you don't have any x's or x cubes, etc. And this is a subring, because if you square any of these two things, you still get even powered terms. But it's not an ideal, because if you take something like this and you multiply it by x, you no longer have just even powered terms. And finally, some ideals. We saw these last time, but I think it's worth seeing them again, especially in comparison to these. So 2 generates a subgroup, but it also generates an ideal, which is the smallest ideal containing 2. And because this ring has unity, we can think of that as all linear combinations of this one element. In other words, all polynomials of the form 2 times f of x. So that consists of the polynomials, all of whose coefficients are even. X, similarly, generates an ideal, which is the set of all polynomials of the form x times f of x. And that is the set of all polynomials that has a 0 constant term. And finally, we can put these together and take all so-called linear combinations of x and 2, and that is polynomials of the form x times f of x plus 2 times g of x. And if you think about this for a moment, you realize that you can let g be 0 and get anything you want except for the constant term. And then you can let f be 0 and g be 1, and then you can get 2, or you can let g be any integer, and now you get any even number for the constant term. So you can get any polynomial that has an even constant term, but that's all you can get, because there's no way to get a constant term that is not even. Finally, here are 2 miscellaneous examples. So this first one is a left ideal but not a right ideal. This is all 2 by 2 matrices of the form A0, C0 over the real numbers. And to see why that is a left ideal, well, if we take A0, C0 times X, Y, Z, W, we get things of the form XA, 0, ZA0. So that is in I. So this is closed under multiplication from the left. But if you take this same matrix A0, C0 and multiply it by X, Y, ZW, now you get, let me write it down here because I have space. Now you have things of the form AX, AY, CX, and CY, and that is not in I. So again, it's a left ideal, but not a right ideal. And finally, our last example is the set of 2 by 2 symmetric matrices in the ring of 2 by 2 matrices. You would think that this is at least a subring, right? It seems like the sort of thing that should be closed under multiplication, but if you check, let's just take a random 2 by 2 symmetric matrix, 1, 2, 2, 3. Let's pick another one. How about 0, -1, -1, 4? So this is -2. We have -1 plus, so we have +7 here, and then we have -3 here, and all of a sudden we have broken the fact that it's symmetric. Those are not the same. So this is a subgroup because it is closed under addition. You add symmetric matrices, it'll still be symmetric, but it's not a subring. I want to finish with what should be a familiar example. We've seen it throughout this course a few times, as early as chapter 2, and that is the Hamiltonians. Now, I don't expect everyone to have seen all the videos, so it's possible you've missed it. So I'll give a very quick recap. So the unit quaternion group consists of I, J, K, 1, and its negatives. Here is the Cayley graph here. So I times J is K, and J times I is -K. And if we allow addition, and also allow there to be coefficients that are real numbers, then that makes them into a ring, called the quaternions or the Hamiltonians. So you can think of this as like extending the complex numbers. So the complex numbers consist of all a plus bi, but this consists of all a plus bi plus cj plus dk. This is isomorphic to a subring of 4x4 matrices over the real numbers. And so you can think of each element here as corresponding to this matrix. We've seen this before. We can formalize this with an embedding, that is a ring homomorphism, from the Hamiltonians to the 4x4 matrices. That sends I, j, and k to these matrices. And we will study ring homomorphisms pretty soon. You can probably surmise what this is from group homomorphisms. And I do want to say several things. So we can also represent these as 2x2 matrices, as we've seen. So I will get sent to I, negative I, 0, 0. So 2x2 matrices over the complex numbers. J will get sent to 0, 1, negative 1, 0. So I will get sent to this. J will get sent to this. And then K will get sent to the product of these two matrices. So that is I. And then, so what is this? This is negative, let me emphasize, this is negative I times negative 1. So that is I here. And you got to be careful because, again, I am always reading things left to right. And I think it's pretty common to read the quaternions from left to right. But matrices, a lot of people read right to left as in function composition. So sometimes you'll see the definitions of these reversed because, again, I'm assuming that this matrix I times this matrix J equals this matrix K, reading them left to right, but some people, if you read them right to left, that's going to switch the signs, SIGNs, of this one here. Okay, I think I'm going to leave things there. Coming up next, we'll learn about several different types of elements and several different types of rings. For example, a unit is any element that has a multiplicative inverse, and a zero divisor is any element that has something you can multiply by, which is non-zero, to get 0. Rings that have no zero divisors other than 0 are called integral domains. They are meant to generalize the integers. Elements that have only units, well, except for 0, are called fields if they're commutative. You've heard that term before. Or skew fields if they're not, like the Hamiltonians. So we'll learn about those, and we'll also learn how to formalize the notion of a quotient ring. And that will lead us right into the concept of a ring homomorphism. So that's all coming up soon. Stay with us.